In this video, we'll review some basics of the stability and compensation of feedback amplifiers. We'll begin by considering first-order feedback systems, that is, feedback systems for which the loop gain L can be written with a first-order single-time constant response, specifically with a finite gain L0, no finite zero in the numerator here, only a single pole in the denominator at a frequency omega p1. Therefore, a Bode plot of L, it looks like this. Low frequency gain L0 that we assume is relatively large, a single pole at omega p1 beyond which the magnitude response rolls off at 20 dB per decade, reaching a unity gain frequency omega t at some much higher frequency, and the phase response begins at 0 degrees and decreases down to 90 degrees. So if you like, you can think of this polar Nyquist plot shown here, and the plot proceeding, evaluating L along the positive imaginary axis causes L to trace out this this Nyquist plot in the complex plane, and since the phase response never goes beyond minus 90 degrees, we certainly have no encirclements in -1. And the bottom line is a first-order feedback amplifier is unconditionally stable with approximately 90 degrees of phase margin when it's just a first-order feedback system. This is very simple, but it's important to keep these things in mind because in a lot of cases, we're going to always have a higher order amplifier, but we're often going to compensate it so that its response is reasonably well approximated by a first order response. And so we're going to use a first order feedback system as a model for more complicated amplifiers in a lot of cases. It's going to be a very simple model, but still useful for building intuition and doing rough hand calculations. So what else do we know about a feedback amplifier with a first order model? Well, if we assume that the loop L has a large DC gain, L0 is large, then the unity gain frequency is very well approximated by just the gain bandwidth product. So omega p1 was the 3 dB bandwidth of L, L0 is its DC gain, but the unity gain frequency, the point at which L drops to 0 dB, is just the product of these two, again, also called the gain bandwidth product. And another good simplifying approximation to keep in mind that's applicable to first order feedback amplifiers is that when you're at frequencies above the pole frequency, that is, omega is much greater than omega p1, the loop gain L is well approximated by this simple response here, omega t over s. So again, if we recall our sketch of the magnitude response of L, whereas it actually looks like this, omega t is over here somewhere, what we're saying is that as long as we're at frequencies well above omega p1, then we can simply apply the simplifying approximation omega t over j omega. So which seems a little strange because it says that L is an integrator, but again, it does look very much like an integrator at frequencies over omega p1 with an integration time constant of omega t. It's just that unlike an integrator, L doesn't have infinite DC gain. So again, at low frequencies, the integrator model would predict infinite gain, but in fact, we're sort of capped at a gain, the low frequency gain L0. Recalling also that the closed loop response is 1 over beta L over 1 plus L. And if we make use of our integrating model here, right, then and substitute that into this expression here, it's straightforwardly simplified to this expression here, which shows some good intuition, which is that the closed loop response is its desired value, 1 over beta, with a single time constant dynamic response, a single pole at omega t, not at omega p1. So again, this is the bandwidth extension that we expect to see the open loop pole at omega p1 becomes a closed loop pole all the way at omega t. So it's really omega t, therefore, the unity gain frequency of L that determines the 3 dB bandwidth of the closed loop response under a first order model. Since the closed loop response is a simple first order single time constant response, its 3 dB bandwidth is given by the pole, but also we would expect it to have a step response that looks like simple exponential settling behavior with a time constant of tau equal to 1 over omega t. So again, first order model of the feedback amplifier is great because once we know omega t, we know really everything we need to know. That plus the desired gain 1 over beta tells us practically everything we need to know about how the closed loop amplifier is going to behave. It tells us its bandwidth, tells us what the step response looks like, um, and interestingly, all of that is independent of the pole, omega p1, the only pole in L. And that's because it doesn't really matter what happens way down here when L is huge anyway, because we know that when L is huge, we basically just have a closed loop response of 1 over beta anyway. So it doesn't matter if omega p1 moves left and right a little bit, gain's still huge there. We still have this ideal behavior. As we said, the first order model is nice and simple and allows us to build intuition and make rough calculations in the back of an envelope really quickly. But practical feedback amplifiers are likely to have many poles and even some zeros. So let's start out by thinking about the complete, like a real amplifier response or a feedback amplifier response where L magnitude response is plotted here with the solid thick line. So it's going to have most likely multiple poles, so therefore it'll roll off, with many breakpoints here. It may, in fact, have zeros, in which case this may bend back up again at some frequencies. But we will see that in order to achieve a reasonable phase margin, we're going to have to compensate amplifiers. We're going to have to force them to have uh, at most one pole at low frequencies, and so therefore we get a unity gain frequency that kicks in at around the same frequency as the higher order poles. So therefore, although it may not, even if a first order model is not applicable, we will apply in many cases with great effect a second order model that captures the low frequency pole with omega p1 and captures the impact of all these second, third, and higher order poles and even zeros with a single equivalent second pole that we will call omega EQ. Now, in the case where omega p2 is much lower than any of the other poles and zeros, then omega EQ will simply equal omega p2. But in some cases, we may have 2 or 3 higher order poles bunched together here around the unity gain frequency. And even in those cases, we can still use a second order model with great efficacy. We just have to choose an appropriate frequency for the equivalent second pole so that the phase response of our second order model follows relatively closely the complete amplifier's open loop phase response, especially over the frequencies that are most of interest to us, that is, those frequencies around omega t, the unity gain frequency. Because it's around there that the feedback amplifier's phase response is being determined. So as long as our second order model properly models the magnitude and phase response, especially the phase response around omega t, then it's going to be useful, a useful model. Now, having adopted this second order model, we can easily relate the phase margin to our equivalent second pole omega EQ, based on the assumption that the first pole, also called the dominant pole omega P1, has introduced a minus 90 degree phase shift by the time we get to omega T. And that's captured by this term here. And then we've got at omega T an additional phase shift here. Let's color it in green. Right, that's the term, the additional phase shift at omega T due to the equivalent pole omega EQ. So this then is the phase of L evaluated. Really, it's an expression for the phase of L evaluated at all frequencies that are far above the low frequency pole. So again, this expression is valid for omegas greater than omega P1. So therefore, we just assume that the phase due to omega P1 is minus 90. But we're going to be, by evaluating this expression at omega T, we're going to be able to relate the phase margin to omega EQ. And that's exactly what we do here. We just evaluate that expression for the phase response of L at omega T, and we rearrange and recognize that the phase margin is just the value of L evaluated at omega T minus negative 180 degrees. And so using these two expressions, combining and rearranging, we get this expression here that relates phase margin to omega EQ and omega T. In fact, it's useful to rearrange this a little bit further and relate the phase margin in terms of the ratio of omega T over omega EQ. So what you see from this expression is that in order to achieve a healthy phase margin, we have to make sure that omega T doesn't start exceeding omega EQ, right? When omega T equals omega EQ, this term becomes 1, and so therefore at that point the phase margin is 45 degrees. So we can, if we have a desired phase margin we want to achieve, then what it means is that we can say, okay, in order to achieve that phase margin, we need to ensure that the unity gain frequency is lower than omega EQ, for example, by a certain factor, by a factor of 2, by a factor of 4, by a factor of 6. And that'll be a function only of the phase margin, that ratio. So here's an example where we're told that an amplifier has a second pole frequency, an equivalent second pole at 50 megahertz, and it's to be used in a negative feedback loop with beta equal 1 and 75 degrees of phase margin. So knowing that, right, for 75 degrees of phase margin, we know that that tangent has to be 0.268. If we substitute in PM equals 75 degrees here, tangent of 15 degrees is here. And so we right away know that if the amplifier has this equivalent second pole at 50 megahertz, the unity gain frequency, and hence the bandwidth of the closed loop amplifier, must be only about 13 megahertz in order to maintain that 75 degrees phase margin. So again, it's a very useful expression for doing very quick calculations of bandwidth, of closed loop bandwidth. And then the other interesting fact that you see is that the bandwidth ultimately of the closed loop amplifier, which is mostly determined by omega t, is in turn really just determined by the second pole frequency, omega t, and of course the phase margin spec. It doesn't depend at all on the dominant pole frequency, omega p1. So it's really this equivalent second pole frequency, omega eq, that's critical in determining the bandwidth of feedback amplifiers. It's the second pole frequency, not the lowest pole frequency. Now, using our second order all pole model for the negative feedback amplifier, you can substitute that in to our expression for the closed loop response and find an expression, a closed form expression for the closed loop response as a function of S, and that's what's done here. And unfortunately, this is quite a complicated expression. It's a little bit difficult to draw any intuition out of it. So it's often rewritten in this form, where we see two terms that have a little bit more physical interpretation. Omega naught is the bandwidth of the closed loop amplifier. And the Q factor is something that is closely related to the amount of peaking in the closed loop magnitude response and the amount of overshoot. And really, it tells us a lot about the locations of the closed loop poles. So specifically, when Q is less than 0.5, we expect the closed loop poles of ACL to be real valued. But once Q exceeds 0.5, then we expect the poles to appear in complex conjugate pairs. Since it's a second order feedback loop, of course, there's only two poles in the closed loop response as well. But when we start, we've already talked about how once these poles go beyond a certain point, then we expect to see peaking in the magnitude, the closed loop magnitude response. And that happens when Q exceeds 1/√2, and so that would, correspond to the poles being located on a 45-degree angle here. That's when we'll see peaking in the magnitude response. Even before that, we will see, however, overshoot in the step response of the closed loop amplifier. And that will arise as soon as we have complex conjugate poles, and that is when Q is greater than 0.5. So obviously Q and omega naught are related to the underlying amplifier poles and DC gains. So that's the connection between the closed loop response, dynamic response, and the loop response L. So these criteria on the Q factor are related to criteria on the phase margin, and in turn related to the ratio of omega t to omega EQ. So this is a very useful table that summarizes what different phase margins correspond to in terms of the ratio of omega t and omega EQ, the Q factor, the resulting overshoot in the closed loop step response of the amplifier, and we've also indicated the criteria for ensuring there's no peaking in the closed loop magnitude response. Now this table, before we talk about it a little bit, it's important to keep in mind that this is applicable specifically and only to second order all pole feedback amplifiers. Again, even when we have more poles and zeros, under certain conditions that we talked about previously, a second order model is still quite accurate at predicting behavior. So the table can also be used for the design of higher order models, as long as we've properly defined an equivalent second pole frequency. So some care is needed there. But again, with a second order feedback loop, then we've already talked about how, to ensure there's no peaking in the magnitude response, we need to ensure a phase margin of a little bit more than 65 degrees, actually, to ensure the Q factor is below 1/√2 in order to ensure no overshoot in the step response, we need to place the Q factor below 0.5. And in order to do that, in fact, what it means is that we need a phase margin of about 80 degrees. So that's, again, back to this point that phase margin is not just a safety margin. If you care about overshoot in the step response to the closed loop amplifier, you may actually require a minimum of 80 degrees phase margin. And then in that case, you may target by design a phase margin of 85 degrees, let's say, just to provide you that extra 5 degrees safety margin in the presence of process voltage or temperature variations. But in fact, the 80 degrees is a hard spec. It's not just 80 degrees of safety margin to stability. The other noteworthy fact that you could see from this table here is that in order to ensure, for example, no overshoot, you are limited to having an equivalent second pole that's, let's say, if this factor is 0.25, that means the equivalent second pole has to be a factor of 4 higher than the unity gain frequency. Or, put another way, omega t, which is the bandwidth of your closed loop amplifier, has to be a factor of 4 lower than the equivalent second pole of L. So this is a big sort of loss in bandwidth, right? You've got a second pole frequency, let's say at 400 megahertz, but it turns out that the closed loop amplifier can only have a bandwidth of 100 megahertz in order to ensure there's no overshoot in the step response. Or in the other case, if you allow a little bit of overshoot in the step response, but want absolutely no peaking in the magnitude response, then, omega t has to be half of omega EQ. So these are good rules, quick rules of thumb that help you determine what kind of bandwidth can be achievable, knowing the equivalent second pole of L. Now on this slide, again, we're reminded that we can use a second order model for higher order feedback systems, again, as long as the magnitude and phase response closely approximates the complete response L, especially around omega t. Now, one way to find an appropriate equivalent second pole frequency when the second and higher order poles and zeros are tightly bunched together is to use this formula here. But in fact, another way that's very easy and practical, especially with simulation, is to just simulate the complete amplifier response, as is, let's say you get a plot such as the one shown here with the thick solid line, and identify the frequency at which that complete amplifier response is minus 135, and then simply define that as omega EQ, because the second order model will also, we know, have a phase response of minus 135 degrees at omega EQ as well. So that kind of ensures that at least, at least in this range here, we've probably got, a decent approximation of the phase response using the second order model. And this brings us to a quick review of feedback compensation. So in general, compensation is the process of modifying by design the frequency response of L so that a desired specification is met. Typically, these are specifications on the dynamic response of the closed loop amplifier, its bandwidth, its overshoot, ringing, peaking, and these can then be translated, as we've seen, into specifications on the phase margin of L, and compensation is just simply shaping L by design to meet that targeted phase margin. Dominant pole compensation is the simplest type of frequency compensation. It's performed by decreasing the frequency of one pole, the dominant pole of L, while leaving, hopefully, the others relatively unchanged. And if we decrease that dominant pole low enough, we end up with a frequency response that, at least up to omega t, is well approximated by our first order model, resulting in an approximately first order system with a phase margin near 90 degrees. And again, there's a lot of desirable properties of first order feedback systems. They're obviously unconditionally stable, but also they have a single time constant settling response, which means there's no overshoot there, there's no peaking in the magnitude response, and so on. The problem with dominant pole compensation is that it's somewhat over conservative. We may, if doing only dominant pole compensation to ensure a phase margin near 90 degrees, we may lower omega t more than we need to in order to meet our specifications, and thereby we may be giving up bandwidth. In some applications, high bandwidth is not required, and so this is perfectly fine on its own. But in other cases, we want to maintain as high an omega t as possible while still meeting our dynamic requirements. So in such cases, we're going to make use of our second order model of negative feedback. And again, we see now that especially once we've introduced some compensation, the phase shift introduced by the equivalent second pole should not be more than about 45 degrees at the most, maybe a little bit more while we're still in the process of doing some compensation. But as long as we have some compensation in there, omega EQ is probably above omega T. So a second order model is reasonable, even if it's a higher order feedback system. And so then the procedure for compensating this second order feedback amplifier is to first find the unity gain frequency that's required to obtain the specified phase margin. And we can do that using this expression that we calculated here. So the idea is that if we assume omega EQ doesn't move, but that we can shift omega T around, where should we put it in order to ensure our targeted phase margin? Well, this expression will tell us that. And again, here's the example we looked at before, where we found that in order to achieve our targeted 75 degrees of phase margin, we need to locate the unity gain frequency at 13.4 megahertz. So then what we're going to do to achieve that is we're going to adjust the dominant pole omega P1. We're going to in fact do some dominant pole compensation in order to obtain the desired omega T. And then the trick that's required from the circuit designer is finding a way to move omega P1 around without affecting omega EQ. Although dominant pole compensation is usually the first tool in our toolbox that we grab to compensate a feedback loop, it's not the only trick. Another common technique that's used to ensure a feedback amplifier has desirable dynamic performance is lead compensation. Lead compensation introduces a left half plane zero into the loop somehow, and generally at a frequency slightly greater than the unity gain frequency. So referring to this plot here, we usually follow a two-step process. Let's say we begin with a response L, like the one shown with the dashed line here. Now in this case, there is a pole omega P1 that's lower than the others, but still, it's not that far away from the equivalent second pole, which is somewhere around here. So the unity gain frequency may be nice and high over here, but if we think about the phase response, the negative phase shift contributed by all these poles is probably pulling the phase response down to around minus 180 degrees. So you may have very little or no phase margin at all, certainly not going to meet any requirements you may have around peaking or overshoot. So the first step with a response like this would be to apply dominant pole compensation and move omega P1 way over to the left, and you may do so targeting the omega T that's required to ensure some targeted phase margin. And let's say you initially target a phase margin of, let's say, 45 degrees. So then you would get the thick dashed line for the phase response and the thick dashed line for the magnitude response. So omega T is now located in such a place where you've got a phase margin of about, let's say, 45 degrees in this case. Lead compensation is then applied by introducing a zero a left half plane zero somewhere here. Now, doing so will give rise to the solid line magnitude response shown here. Because we've introduced the zero, the magnitude response will bend up slightly and may counter the extra roll-off introduced by the equivalent second pole. Eventually, third, fourth, higher order poles will kick in, and we expect the magnitude response to start dropping more sharply again. Keep in mind that when you actually plot these things, you're not going to observe sharp corners such as I've shown here in this piecewise linear approximation of the Bode plot. Everything will be rounded, so it may be less clear from the Bode plot exactly where these corner frequencies are. This is just a cartoon to illustrate the point, but certainly introducing the lead compensating zero will cause the magnitude response to bend up a little bit. That's why we do so at a frequency above omega t, because we don't want to disturb omega t too much. However, even at a frequency below the zero frequency, specifically at omega t, the lead compensating zero, since it's a left half plane zero, will introduce some additional phase shift. So that's the reason why we apply the phase margin. It actually will give, why we apply lead compensation. It actually gives us a little bit of an extra phase margin without having to further sacrifice bandwidth as we would have to if we used only dominant pole compensation. To say that another way, if we used only dominant pole compensation to achieve that same extra phase margin, would have required us to move omega t even further to the left and would have caused omega t to shift even further to the left. Now we didn't want to do that, and we don't want to give up any more bandwidth, so we just used lead compensation to introduce this additional little boost of perhaps 15 to maybe 30 or so degrees of extra phase margin without sacrificing omega t. In doing so, we make the closed loop response more complicated because we've introduced a zero now. It's no longer just an all-pole response. Um, but again, since the zero is at a frequency above omega t, where our hope is that it doesn't significantly change any of our desirable dynamic properties.